Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 14.2, day 2, entitled Probability. And today we're going to finish up our objectives. We're going to talk a little bit more about unions of events, but mostly in terms of the conditional probability and the intersection of events. So for conditional probability and intersection, this is basically where you have dependent events or independent events. So for this first definition here, this is where we're dealing with a dependent event. And what that means is that the first event depends upon the other, or actually the second event depends upon the first. So this is where you would have a bowl full of M&Ms, let's say, and you reach in and you grab a red M&M and then you eat it. And then you reach in and you grab another one. So after you've eaten that first M&M, you've reduced the total sample size that you have to choose from when you're selecting your second M&M. Okay, so that second M&M depends upon the selection of the first one. Okay, so this, we can also think of it as where this is without replacement. And replacement is when you put something back. So here we're not replacing the M&M. We're reaching in, we're grabbing the M&M, we're eating it, and then we're reaching in and we're taking another one. We're not putting the M&Ms back. Okay, so then here we're going to have our intersection of those two events. Okay, picking the first M&M and picking the second one. So you have the probability of the first times the probability of the second given whatever happened in the first event. Okay, so here let's take a look at an example where we're dealing with cards instead of with M&Ms. But here we have two cards that are being drawn without replacement. There's that key phrase. So that tells you that the events are going to be dependent. Okay, so two cards are drawn without replacement from a 52 card deck. Find the probability of the following. The first card drawn is an ace, and the second drawn is a king. Now, drawing an ace isn't really going to affect the number of kings that you have because they're not the same card. But after you draw that ace, you're not replacing it. So then you have fewer cards to choose from to get that king. Okay? So again, this is dealing with cards, and if you don't know how many aces are in a deck of cards, there's 4. There's 1 for each suit. Okay, so when we're choosing that first card, we'd have 4 out of 52 options. But then you keep that ace, so you've reduced the number in the deck of cards by 1. So now there's 51 total that you have to choose from. But there's still 4 kings, so now you have 4 out of 51. But keeping that ace in your hand and not putting it back in the deck of cards changes how many you have to pick from. Okay, so now when we multiply across, we'll get 16 over 2,652. And we can reduce that down to 4 over 663, or you could write it as a decimal, 0.006. So a very small chance of that happening where you draw an ace and then a king. Okay, so let's look at our next example here. Now the first card that's going to be drawn is going to be an ace, and then the second one is also going to be an ace. So again, we've got 4 aces out of the 52, but now you're taking that ace out of the deck and you're holding it in your hand. So you've not only reduced the number of cards that you have to choose from, you've also reduced the number of aces. So instead of having 4 aces to choose from, you now have 3. So that can happen as well, where you're reducing the total set and you're reducing the event as well, the number of possible events that you want. Okay, so here we'll still multiply across. We'll get 12 over the 2,652. And then we can reduce that to 1 out of 221. Or if you want to write it as a decimal, 0.0045. So an even smaller chance of that happening than if you draw an ace and a king. Okay, so the important thing to notice for these two examples is that the second event depends upon the outcome of the first event. So it's going to affect either how many events you have that you want in your numerator or the total number of set events in the denominator. Okay, now the other option or the other example that we have to look at is when we have independent events. Okay, so we can still have an intersection, but when they're independent, that means one doesn't affect the other. So your probability of one event happening and your probability of the other event happening, they're exactly the same. So this would be like you have a bowl full of Starburst candies, and you reach in and you grab one and it's a yellow, and then you decide, oh, I don't want the yellow. So you put it back into the jar and then you pick out a strawberry. Okay? So these are independent events. Your first one didn't affect your second one. So since these are independent, the probability of the first event doesn't have any effect on the probability of the second event when they're independent. And it's independent because there is replacement. So this is where you would pick a card from a deck and then put it back and then pick another one. Or like I said with the Starbursts, you would pick one, decide you don't want that one, you put it back, and then you pick a different one. Okay? So you're just going to take the probability of the first event times the probability of the second event. And this is still an intersection because it's multiple events going on. Okay, so let's look at our last example here. We have a jar that contains 5 red balls and 4 black balls. So that's important to know that we have 5 and we have 4. So that means altogether we have 9. Okay, so we have 9 total. And a ball is drawn at random from the jar and then replaced. So there they tell us that it's replaced, so we know these are going to be independent events. Then another ball is picked. So what's the probability that both balls are red? So we want to find the probability of drawing a red and then another red. Okay, so the red ones, we had 5. So we reach in and there's 5 options out of 9. So we reach into the bowl containing all these balls, or this jar, pull one out, and then we put it back, and then we pull another one. So we have the same chance again, 5 out of 9. So if we multiply across, we get 25 over 81. And I don't think we can reduce that down, but we can write it as a decimal, 0.309. Okay, so about a 30% chance of that happening. So not too shabby, not super duper great, but it could happen. Okay. So the key to remember in this homework assignment is to just pay attention to the problems, read them carefully, look for that key phrase of replacement or without replacement or no replacement. So that way you can identify if it's an independent or a dependent event. If they're independent, you just find the probability of each and multiply them. If they're dependent, then you have to subtract either from the numerator or the denominator of that probability for the second event. So take a look at the odd problems in the back of the book. Remember, the solutions are worked out on the class website. And if you have questions, come on in and see me before school.